Hello and welcome back. In this lecture, we learn about the concept fluid pressure. Pressure is a fluid property. To better understand this concept, let us quickly review a sub-concept that can be related to it. We have seen earlier that, when a body is subjected to compressive, tensile or shear forces, stress develops inside the body. The magnitude of average stress, in a given area, is the ratio of force to the area. We can imagine similar situation for a fluid. Consider a container with some fluid inside, say air. Imagine that, using a piston assembly, we can apply force to the air inside the vessel. Let the area of piston is 2 meters square, if a force of 100 Newton applied to the piston, and if it is in static equilibrium, there must be some force acting on the piston from the fluid. Pressure is the term used indicates normal force exerted by the fluid per unit area at a given point. It is similar to the term stress we have seen earlier. Let P be the normal force exerted by the fluid per unit area of the piston. Now, P times area of the piston must be equal to 100 Newton. Or pressure, P equals force divided by area equals 100 divided by 2 equals 50 Newton per meter square. Microscopically, pressure is the average reactive force exerted by molecules on the walls of the fluid container, due to its collision and resulting change in momentum. Pressure at given point in a fluid is discussed next. Consider the previous example. We have seen that a force applied on the piston generates pressure inside the fluid. Assume the fluid is static. This means it is stationary and not flowing. We will see the meaning of pressure at a given point in the static fluid in this example. To better understand this, consider a differential volume element of air within the continuum approximation. Imagine that air surrounding this volume element exerts force on each side of this element. This force per unit area is the pressure exerted by the fluid on this imaginary, static fluid element. Since the element is in static equilibrium, we can show that the pressure acting on this fluid element, from all surrounding direction is same. That is, pressure at a point in a fluid at rest, is independent of direction. This important result is known as Pascal's law. Although pressure acting at a point in a static fluid is same from all directions, it will change from one point to another. We will see how this variation of pressure happens in a static fluid. Consider again a fluid element, in the previous example. The forces acting on this element are the pressure forces from the surrounding fluid, and the weight of the element. It can be shown mathematically, using the static equilibrium conditions, that for a static fluid, pressure varies only in the vertical direction and remains same at same horizontal locations. In this case, pressure at location 3 is same as pressure at location 1 and it is different at location 2, at a different level. Atmospheric pressure is weight of air column, per unit area above the surface of the Earth. The atmospheric pressure is roughly extends to 10.3 kilometers from the surface, and it weighs nearly 100.9 kilonewton per meter square, on Earth's surface. Approximately, the value of atmospheric pressure on the surface of the Earth can be calculated as 101 kilopascals. Consider a static fluid with free surface. Let it be water. Let us see how pressure varies in this static fluid. At location 1, the interface of fluid and atmospheric air, the pressure is atmospheric equals P1. This is approximately equal to 101 kilopascals. We saw earlier that pressure varies only in the z direction. Since pressure depends only on variable z, this equation can be integrated from one location to another. Finally, we can derive an equation that connects pressure at the free surface to a different point in the fluid, at a depth of h, P2 equals P1 plus raw GH. Consider a practical situation. Water is stored in a dam as shown in figure. Calculate the pressure at 3 different locations. We know that pressure at location 1 is the atmospheric pressure. To calculate pressure at a different location, we use the equation derived earlier. Using this equation, we can calculate the pressure at a depth 25 meters and 125 meters. Assume the density of water as 1000 kg per meter cube. Average ocean depth is approximately 4000 meters in the Pacific. The deepest place is 10,000 meters down the free surface. Calculate pressure at these depths. Assume atmospheric pressure is 101 kilopascals. Density of seawater is 1.2 kilograms per meter cube. Using the previous equation can find the pressure at these locations. Now we know that pressure at these depths is dangerously high. We will solve this problem in class. Finally, here is a summary of the key concept of this video. The pressure at a location in a fluid can be related to the pressure at a reference location in the fluid, density of fluid, gravity, and the distance between the two locations. Thank you for listening.